So thank you very much, Ulrike, for the introduction, and also I'm happy that you have made it here and that we can hopefully have a nice weekend and more, and to learn a bit about lower semi-continuity and integral functionals and applications. So it's a favorite topic of mine for many years, and maybe I would like to give you a little bit of history. I mean, how this developed. So it's also related to Prague. So around 1830, Bernard Bolzano who, by the way, worked at the Charles University in Prague, and he has a grave there. I mean, not at the university, but in Prague. So if you come to Prague, I think it's also quite visited place, at least for people interested in history of science. And there is a street of Bolzano close to the main station, so it's one of the places you can rush into when you come. So around this time, he proved that a continuous function on the closed interval 0, 1 attains a minimum. And so the main tool to show this was the result, which is nowadays called Bolzano-Weierstrass theorem. And simply this means that if you have a sequence which is in this interval, you can pick up a convergent subsequence. So this is via Bolzano Weierstrass theorem. But it already set up a strategy which we use till these days, and only it's moved to some infinite dimensional spaces and so on. But the main idea is so the idea was to consider a minimizing sequence So if the function is called f, so I take a sequence fxi such that fxi converges to the infimum of f on this interval 0, 1. So the limit for I going to infinity. And so that's the minimizing sequence. So it's called minimizing sequence. Notice that even so we don't know whether there is a minimizer yet. So it should be called like infimizing sequence. But it's a little bit abuse of the notation. And now once you have it, then you take the sequence xi and this is a point 1, this is point 2, and pick up a converging subsequence. And as we normally do in mathematics, we do not relabel here. So we say xi converges to x. And the last point is that you use continuity to show that fxi converges to fx. But this also converges to the infimum of f. So this implies that f of x equals the infimum of f on, say, 0, 1. And this is the proof that there is a minimizer. And the same algorithm or scenario was suggested by David Hilbert around 1900s. Together with Ries and also Stanislav Zaremba. And Hilbert suggested to proceed like that, or similar like that, not in finite dimensional spaces or closed intervals, but in Hilbert spaces, or what is nowadays called Hilbert spaces. To say complete spaces with the dot product, say. And later, around 1940, Stefan Banach upgraded this procedure to Banach spaces. So this is always like around yeah, so and this is what we have now, roughly. There is an, I mean, if you want to read about these developments, there is a nice book by Albert Peach. And it's called History of Banach Spaces. And applications. I think it's Springer around 2007. It's a nice book, so about all these developments. So now it looks very easy for us to work in Banach spaces, but of course it was a big step forward. And so what I want to say is here that here we use continuity, continuous function. Here it's not a big deal to weaken this assumption to go for lower semi-continuous functions, but in infinite dimensional spaces it's a big difference. So instead of continuous functions, we work with lower semi-continuous functions. What in this setting would mean that limits inferior I goes to infinity of x, I would be bigger or equal than f of x if xi goes to x. And I couldn't trace in the literature who made this step from continuous to lower semi-continuous, which look very easy here, but it's very important here. So instead of working on a closed interval, of course, you can say that your function is coercive. It means that at the end, you can also restrict yourself to some bounded and closed set, say in 0, 1, or compact set in a suitable topology in these infinite dimensional spaces if you want. So instead of, so this is a generalization, say. So what we, so the algorithm works like this. minimum of some, now let me say that we work with functional, so it will be I, which will now go from some Banach space to reals and maybe included plus infinity. So first, consider a minimizing sequence. UK, which belongs to this Banach space, and such that I of UK converges to the infimum of I over this Banach space. Now this is an important point, so show that UK in this Banach space B is bounded by some constant for every K. So it's a uniform bound. This allows you, and this is important, so if B is reflexive, for example, we can pick up a weakly converging subsequence. Subsequence such that UK converges weakly to U in B. And this is somehow maximum what we can hope for, because typically you cannot expect that from this condition you would get strong convergence of a subsequence. So weak or weak star convergence is something this is the optimal, or at least kind of a maximum what we can get usually. And now this means that if I is sequentially, so which will be for us typically the situation that sequential weak continuity is the same like weak continuity. If I is sequentially weakly, our semi-continuous, then we can conclude that which means that lim inf of I of UK is bigger or equal than I of U. For this sequence, then we can say that there is a minimizer. So that's the scenario. And then in particular cases, you have to somehow check all these steps. And as you can imagine that I can find a minimizing sequence from the definition of the infimum. This one I can hopefully make by assuming some coercivity. So my functional is bigger than something if the norm of my argument is bigger than something else. B is a Banach space, which I say is if it's reflexive, so this is my choice. So hopefully I can set up a problem in a reflexive Banach space. But the difficult part is exactly this. To be able to, maybe I put it higher, to be able to isolate conditions that tell me that my functional is weakly Lauer semicontinuous. So maybe we now can define it. So we say that I from B to R is sequentially weakly Lauer semicontinuous if for every UK in this Banach space such that UK goes weakly to U in B, it holds that lim inf I of UK for K going to infinity is bigger or equal than I of U. Now your question can come and you can say, oh, why do I need this property for every sequence like that? It would be enough to have it for a minimizing sequence. This would be enough. I don't care about other sequences. But it's also difficult to say, to kind of characterize minimizing sequence in a sense. And there are some papers for particular cases that in fact they show that the property which we need on I is the same in some particular cases. So for the algorithm to work, it would be enough if this property holds only for minimizing sequence, but here we do it in a more general way, so we have a stronger condition. Also, what's a little bit tricky, and I want to call your attention to it, that weak Lauer semicontinuity is stronger than Lauer semicontinuity with respect to norm convergence. So it's a little bit confusing. We have weak Lauer semicontinuity, but in fact it's stronger. And this is simply because if you have a sequence like that, which is weakly converging only, that can behave more widely, you have less control over the sequence than if you know that the norm, that there is norm convergence. So this is important to remember. So it's a remark. So WLC is stronger than norm Lauer semicontinuity. And this would mean that I replace here this half arrow by full arrow. So this program is called the direct method of the calculus of variations. And if you search for some sources of information, so I collected a couple of sources for you here. There is a book by Bernard da Coruña, which is called the direct method in the calculus of variation. And this is the second edition, Springer 2007. It's a thick book. If you want to go for something thinner and less demanding, then we have a survey article with a colleague of mine, Barbora Benešová. And this is called weak-Lauer semicontinuity of integral functionals. And applications. And this is SIAM review. (2017). There is a book by Tomáš Roubíček, for example, where you can find some applications of this direct method of the calculus of additions to PDE analysis. And this is called nonlinear PDE. And applications. And this is Birkhäuser. (2013). There is a book by T.R. about mathematical elasticity, where this direct method is used a lot in application. So and this is volume 1, and this is 1988. And there is also a book by me and Tomáš Roubíček on this is called Mathematical Methods in the continuum mechanics of solids. And there are many other, and of course, many papers on this topic and so on. So this is, I mean, a rough survey of, say, available literature, which you can have a look at. And I also will prepare notes. I mean, I just did some corrections in the train yesterday, so I will send you some notes where all this will be somehow. So lecture after lecture, I will give you some study material. So this is about the literature. And let's go for something practical. So first of all, now if you have it like that, you can say, is there any functional? I mean, how do I recognize a functional which satisfies this property? So it means, I mean, is there any property I can just verify easily and say this will be weakly Lauer semicontinuous? And this is indeed the case. So the proposition so let B be a Banach space. let I goes from B to R included plus infinity. So sometimes we will see that it's very useful if the functional can also take plus infinity. So that's why we included here B convex and lower semi-continuous. Then it is weakly sequentially lower semi-continuous. So this really look like a easier condition, because you say if my functional is convex and lower semi-continuous with respect to the norm topology, then it will have my property. Before we do the proof, we discuss a bit whether this convexity is really necessary, and whether if I don't have it, I don't know, I mean, how is the relationship of convexity and the lower semi-continuity? So we see it's a sufficient condition here. If you don't have plus infinity here, you can forget this lower semi-continuous, because convex functions are continuous. So this is just here to be able to include plus infinity. So let's take the following functional, very easy in 1D, so there are some remarks. Maybe I can say some remark that first, we don't have to work on the whole space, because sometimes, for example, you can imagine that you have some problem where you have, say, boundary conditions or something like that. So it would be much better for you if you can work on some subset of the Banach space. So we don't have to work on the whole B. It's sufficient if we find a weakly closed subset of B. So weakly closed means if I have a weakly converging sequence in this set, then also the weak limit is there. Because if your limit is not in the admissible set, then somehow you are in trouble, because you want to show that you find a minimizer on the set. So think about problems with boundary conditions. So this, and then you proceed the same way, because if you know that your sequence and the limit are in some subset, then you simply minimize only over the subset. So consider the following example. You take a very simple functional, which will be the integral functional on 0, 1. And this will be u squared f plus u prime of x minus 1 to the power 2 dx. So prime means derivative. And then you assume that you want to minimize this functional, which is now defined on the set A to R, and A, the set of admissible deformation, the admissible test functions will be u in W14, 0, 1. So 4, because we have u prime here in the power 4, it's a second, so it's a Sobolev space. I hope you are familiar with this notation. And then we assume that u0 is u at 1, and this is 0, and we also assume that u prime is between 1 and minus 1. I take a set like that. And so what we see first is that I is not convex. So the observation is that I is not convex. So we cannot apply the proposition. But still we can search for a minimum, because this direct method gives you kind of technology how to show that there is a minimizer, but if you cannot apply it, it doesn't mean anything. So let's try to find a minimizing sequence. UK, which will belong to my set A. So you look at a functional, you inspect it a bit, and you say the first term is happy if u is small, the second term is happy if u prime is plus or minus 1, because u squared minus 1 has to be small. So this is your interval 0, 1, and then you go with your u1 like a test function to 1/2, and then you go back here. So the slope is 1 and minus 1. So slope is 1. So you arrive at 1/2 here. And then here is, this is u1. And I can evaluate u1. The first term will give me something. The second term will give me 0. So I will not do it, but you can imagine you can do it. You can proceed like that. And we can also do a finer construction. So we go with the slope 1 here, and then we go with the slope minus 1 here, and we do the same here. This will be u2. Again, the first term will give me something, but now less than before. And the second term gives me nothing, because again, the slope is plus and minus 1. So I know that u2 is more than u1. Or maybe I say that I is bigger than 2. And then any one of us can come to the blackboard and pick up its own function. So you go again to the middle here. You go down and here like that. So again, you do the zigzag function with the slope plus and minus 1, which starts here and arrives here. And you do it the same here. And this will be u3. So again, by the same argument, you get something which gives you smaller contribution. And then you can repeat this construction infinitely many times. What you can already guess from the construction here is that the limit of those values will be 0. Because the second term doesn't give you anything, the first term gives you smaller terms. So we can say that lim of I of uk, k goes to infinity, is 0. And this is the infimum of I over my admissible set, because this is a non-negative integrand here. So whenever I arrive at 0, I mean, this is the optimal value. But the question is there any minimizer? So it means, is there a function u which would give me 0 as a reply if I plug this function to the functional, as a functional value? Not, because this function would have to be 0 because of this term, and the slope must be plus or minus 1. So there is no function like that. So the infimum is 0, but there is no minimizer. So this somehow shows that if I give up convexity, sometimes, at least in this example, I may come into a contradiction that there is a minimizer of my functional. So now I can hope maybe this is if and only if, like, if I don't have convexity, I have never a minimizer. But this is not the case. Because you can imagine that you suddenly change your A. So we change the admissible set to say A tilde, and this will be almost like before. But I say u at 0 is 0, u at 1 is 1, and minus 1 is smaller than u prime, and this is smaller than 1. So again, the picture looks like the following. So there is 0 here, there is 1, and I know I start from here, I have to arrive at a function value 1 here, and the slope cannot be bigger than 1. So I only take the linear function. That's the only choice. So this is ux equals x is the only possibility. And consequently, I has a minimizer on this set. There is no other choice. So it shows that boundary conditions are very important in this business. You can simply change it a bit and the result changes completely. So even if you have a non-convex functional, you can arrive at a problem which has a solution. So convexity is definitely sufficient. but it's not necessary. Maybe I erase it, and then we look at the proposition and whether we can prove it. Will you record also erasing the blackboard? Okay, yeah. It's fun for people in the audience. You want to, maybe we need a proposition, but otherwise, maybe. No, because this functional is not convex, because if you take U1 and U2, you take a line between them, and you look at the functional values between, so then you show that this is not the case. So there is nothing more than just normal convexity. Yeah. Maybe it's better, you think? I think it's better, yeah, maybe, but then it is for drying. I think it's not for, I was wondering whether for drying there is this wiper, and this is for, yeah, you can take it off. It's a dry washing. You know, I'm not a big expert, but we use this for wet washing. Maybe I just do this, and then we go on, and then later we clean this one. sorry for the delay. This is just too big room and two big blackboards. And so now we want to prove the proposition which I kept here. So proof so the convex functional, so convex analysis will be important, particularly the Hahn-Banach theorem is behind it. So we take UK in B, a general sequence such that UK weakly converges to U in B. Here I for K going to infinity. So here notice that I don't really need reflexivity because I already have a sequence. I'm checking the property. It's not about checking the existence of minimizers, but it's just checking the property. So I already am given the sequence and I want the sequence which converges to some U. And now we look at the functional. So, and we want to show I of UK is bigger or equal to I of U. This is what we want to show by the definition. So the first thing what we do is that we replace this lim inf by lim. So we pick up a sequence which makes it so. And I do not relabel the sequence. Take a subsequence. Of UK. Not relabeled, such that I of U is smaller or equal than lim I of UK. And let's say that this is called L. And now there is a lucky case and a worst case. So the lucky case is that L is plus infinity. If L is plus infinity, of course, then it's super because then and there is nothing to prove. So this is maybe A. So B, could it be that L is minus infinity? This would be bad because then I would have minus infinity here. And if I of U is not minus infinity, then I'm in trouble. L cannot be minus infinity. This is what I say. Why? Because, I mean, it's a convex functional. And I don't know how much you have heard from convex analysis, because, for example, in Prague, this is something which is generally not really well presented. But there is something like there's a convex function in general, and you have a Hahn-Banach theorem. There is always some affine function below that. This is related to separation of convex set by hyperplanes and so on. So, but this will help us here, because we know that there is a because an affine functional below, oh, I'm sorry, below I. So now I go here. So here that I of UK is bigger or equal than this functional, which maybe I call psi of UK. And this is bigger or equal than minus norm of psi in B prime times the norm of UK in B. So that's the estimate. This is a given there's a affine function of psi. So I put psi here below I. So this is a given functional independent of K. There are many of them. I pick up one. And UK here is a norm. But because this is a weakly converging sequence, then the weakly converging sequences are bounded in norms. So this is bounded. So this is bigger or equal than minus psi in B times some constant C, where supremum over K of my UK in B is bounded by this C. So, fortunately, the bad case is excluded, and what remains is in between, and we have to work a little bit here. So L is finite. Yeah. So this is, I mean, no, we did the limit. So we did not, so first what you do, you have your sequence, you have lim_inf here. So you pick up a subsequence which makes the lim_inf. And you say, now this is lim. And this limit, this is a number. It's called L, like a limit. And then it's a real number, maybe plus infinity or maybe minus infinity, you never know. And so you try to decide what it could be. L plus infinity is possible, but it's fine, because if this is plus infinity, then whatever I put here, then this inequality holds. So I'm happy. L equal minus infinity would be a troublemaker, because the only choice would be that I of u is minus infinity here. Otherwise, it doesn't hold. So, but here I say that it's not possible, because it's a convex functional. If we have a convex function, so there's always an affine function below. And so this tells you, and because my sequence is bounded in B, that I have this, and this is a given number. Negative perhaps, definitely negative, but fine. So L is finite is now the last possibility. Everything in between. And so what shall we do here? So we have this limit. So we say, so take epsilon positive. It always starts like that, these mathematical proofs, right? So then there exists K0, a natural number, such that I of UK is smaller or equal than L plus epsilon if K is bigger than K0. So that's the property of the limit. If everything is above L plus epsilon for some epsilon, then the limit cannot be L. So now we used, so here we used convexity of my functional, and here we haven't yet, but we will, because I mean that's a key property. Convexity always is a key property. So now we need to use convexity. So how to use convexity? So the convexity used via the so-called Mazur lemma. Have you heard about Mazur lemma? No. So Mazur lemma is something what roughly what improves the convergence. It's a consequence of the Hahn-Banach theorem. And there is an original paper by Stanislav Mazur, written in German. And it says, if you have a weakly converging sequence, like we have, then it can oscillate a lot in general. But you can take averages, weighted averages, such that these weighted averages converge to the same limit as is the weak limit, but the convergence is strong. So, Mazur lemma and the Mazur lemma says that I construct a sequence Wj, which will be defined like that. K is from J to infinity, lambda Jk Uk. And the coefficients lambda Jk are the following, have the following property. So lambda Jk are always non-negative. If I sum up lambda Jk over k between j and infinity, then I get 1. And only finitely many lambda Jk as a sequence in K are non-zero. So you have finitely many, you do convex combination over finitely many elements, and you create this sequence. And the claim, the Mazur lemma says that then Wj converges strongly to U in B. So it's somehow, weak convergence is a convergence in average. So somehow the weak limit is the average of all. So if you already average these elements, there is a hope that you arrive at the limit in a strong way. So that's the result. So maybe I should emphasize that this is strong. So now what we do, we say, okay, so this convergence is for J going to infinity. So now I look at I Wj. Because Wj converges strongly, and my functional is lower semicontinuous in the strong topology. So if I pass to the limit with J, then I would know that this lim inf of those would be bigger or equal than I of U. So I can put here I of U. But then I need a limit, and this is so maybe I do it here. So let's put here Wj. Now we say what's Wj? So we say this is I of sum over k between j and infinity of lambda jk, sorry, uk. And now the charm comes, because here you have a convex functional and you have a sum of convex combinations inside. So you take it out and make it bigger. And lambda jk I of uk. And we know that this is because these are convex coefficient, convex combination coefficient. So they sum up to 1, and we know that I of uk is smaller than L plus epsilon. So this is smaller or equal L plus epsilon. And now I pass to the limit for j going to infinity. So for j going to infinity. And then here you still have the bound, and here you get, because of the strong lower semi-continuity, that the left-hand side is, you get I of u is bigger or equal than lim inf of I of wj for j going to infinity. And this is bigger or equal than L plus epsilon. And because epsilon was arbitrary, it has to be like that for. So the claim is proved. The claim is proved. Because epsilon was positive but arbitrary. So this somehow is a combination of convexity and strong Lauer semi-continuity. That's it. So and we should really be happy because convexity, this is something what really helps because of this. And we will see later that we would be happy to have it forever, but we cannot. So now we can, so example which can be so example is, for example, something like that. So you have I of u, so typically some integral function of f of u x dx for f convex. So if you from if you are here in some Rm to R convex. So now you can apply it to these kind of problems, for example. Or you can replace u by a gradient of u if you want, or higher order gradients, or you can even put x here. So you can say I of u might be an f, which now goes from omega times Rm, R is such that f x, so if I fix x, is convex and f dot v is measurable for every v and here for every x, almost every x, for almost every x and for every v. So this already sounds like a Kara-Theodori integrand, if you want. So this is an example. So you have many functions, and this is an example where you can apply this theorem. So now maybe I can erase a bit. Maybe I keep this and I erase here this piece. You can finish your writing, you can think about it. So now you say we are done because we take convexity, and this is something what will help us to show the existence of minimizers. But I mean, because we should speak also about applications, there are applications where convexity is not really a suitable property. And then what I always say, it's this elasticity, because elasticity is when the calculus of variations meets reality or meets mechanics. There's lots of friction in between. Because mathematicians come with some ideas and physicists with different, and now they have to somehow go along. You know, if you, it's a brief excursion to say elasticity. So what we do in elasticity, you have your domain omega. This is your reference configuration. This is like this sponge. This is my sponge. This is my reference. This is omega. Now you apply some forces, boundary conditions or something else, and you deform it. And you get a sponge deformed, and this is something else here. And in between there is a map, which maps the original sponge to this deformed sponge, and this map is called typically Y, and so this is Y of omega. This one is a reference configuration. And this one is a deformed configuration. So Y goes from omega, which in elasticity is a three-dimensional thing, a subset of R3, and it's a bounded set with a Lipschitz, the domain with the Lipschitz boundary, say it mathematically, but you can think about the sponge. And this again goes to R3 because, you know, you don't change dimensions. And this is called a deformation. And so the functional, which typically appears in this elasticity problem, is the following. So you take J, because now it's J of Y. It's the integral over omega of W, may depend on X, but doesn't have to, so I forget this dependence, of the gradient of Y of X, Ex. And this W is something what I call stored energy density, and it means if I deform this sponge, I am putting some energy. I mean, to do that, I need to put some energy to this body. This energy, if you think about a spring, is stored there. In an ideal situation that there are no energy losses, I can use it later. Like if you have a spring or a piece of a rubber, then you extend it, and then you know you can use it for future usage, like you have some popular or so, like a kit for as a toy and so on. So this is called stored energy density. So now this is a function which is defined on matrices, because if this goes from R3 to R3, then this is a gradient, and this is a matrix which is and I say that it will go to R plus infinity. It's called stored energy. Stored energy density. So if you are into physics, so the unit is Pascal, because the whole thing is the energy, and you integrate over the volume, so it's Pascal. So Pascal is the density of energy, joule per cubic meter. So so now you want to find, you know, if you apply some boundary conditions, for example, you say this phase moves somewhere, then I apply boundary conditions. So I say I deform the body in a way that the boundary is controlled. Then I look for this functional, what the value of this functional on this deformation, and I try to minimize it. There is a minimization principle which tells me this, the stable configuration will be the one which minimizes this energy. That's the physical motivation behind it. So we want to minimize J, on some suitable class of deformations, on some class of deformations. So now we already know that if W is convex, then the functional would be convex, and we can proceed. But the trouble is that you come to physicist, and he says it cannot be convex. And the reason is the following. So there are some physical requirements on W. W cannot be convex. Because of the following reason mainly. So if you deform your sponge to a point, then you are, you know, like want the sponge to disappear, it means you are decreasing the volume a lot. So then the energy has to grow because nobody wants to be squeezed to a point. So we assume, so the assumption which is needed here from the physical point of view is we must assume that W of F goes to plus infinity if that F goes to 0. This F is a matrix. Further, we assume that from the physics again, that the determinant of F, which means the determinant of this gradient of Y, has to be positive. Because if you imagine that it can change the sign, then it would allow for something completely non-physical. Like if you take now we go from 3D to 2D, you take a square like this, so this is 0, 0, this is 1, 0, this is 1, 1, and this is 0, 1. This is my omega, and now I apply the deformation y of x is minus 1, 0, 0, 1 times x. So the affine deformation, which is such that the gradient has a determinant minus 1. So it means that you would say you flip it over here, but you cannot do it because you are only in the plane. So it means you go through the body here and you turn it upside down. So this is not possible. So we assume that, so we have this assumption. And then we have also another assumption which says that W of f is plus infinity if that f is smaller or equal than 0. If that f is 0, it means I'm losing volume. And you don't want this. So simply you say that to do deformations like here, which are unphysical, I need infinite amount of energy. So it's not possible. So this is a physical assumption, and this is a physical assumption, which we have to keep in the model. If you really want to do something real, you have to take this into account. So let's look for a convex function which satisfies this and this. So I take, for example, matrix 1. So A1 will be -1, 0, 0, 0, -1, 0, 0, 0, 1. It's determinant 1, so it's fine. And A2 will be just the identity matrix. So now the property of convex functions is that if you take the line segment and you look at the convex function on this line segment, then if you take a maximum of the function values at the endpoints, they always bound everything inside. So if W is convex, then W at lambda A1 plus 1 minus lambda A2 is smaller or equal than lambda WA1 plus 1 minus lambda WA2. And this is smaller or equal the maximum of W at A1 and W at A2, because lambda is something between 0 and 1. Oh? That's the property of convex function. So now A1 and A2 are matrices with positive determinants, so the determinant is 1. So we assume it's a finite number. But in the middle, like if you take lambda 1/2, you are -1 here, but at identity you would have 1, so you get something which is 0. So the determinant would be 0. So if lambda equals 1/2, then lambda A1 plus 1 minus lambda A2 is not invertible. Hence, W as this matrix is plus infinity. And because if you approach this point lambda equal 1/2 from the left, then you are going up because of this property here. So it means it cannot be convex. So convexity is excluded. I have to say that this concerns mainly of the part of elasticity which is called large strain elasticity. So if you do linearized theory like at high school with Young modulus and these kind of things, then you can still be in a convex framework, but this doesn't describe some problems. For example, if you do some buckling, if you have a sword, you push it against the wall and it buckles. Because in particular in linearized elasticity, you have typically a unique solution. Well, if you do this buckling, you never know whether this buckles up, down, or to the left or right. So we have to use this approach in case of some physical models. So convexity is excluded. This means that we cannot really apply our proposition, and we are again in the beginning. Yeah, so now because it's not needed anymore, I erase the proof. Yeah, these, yeah. It cannot be. Yeah, but I can always do this. I mean, if I have convexity, then I can always test my convex function on these two matrices. Yeah, but this is special subset of Y's. This will be a special subset of Y's. For example, I prescribe boundary conditions. But how can you make sure that even in the special subset of Y's, you don't create some example like that? Yeah. So somehow convexity, I mean, you can, this is a property, so this is a property of the deformation or a class of functions which I allow to be my deformation. Well, this is a property of the W, like a material property. This is a material property. So if this is like something which comes from, say, measurements or some modeling assumptions, while this comes from some experiment setting. And I can do various experiments on the same material. And then if I have the same material, I want to use the same W. Does it answer your question? There are some other properties which I don't want to mention here because it just would need more background. In small strain? In small strain it can be, it typically is. But it's typically strictly convex even. So you have uniqueness of minimizers, but then you have experiments like if you take this and you push it against the wall, if it's thinner, it would buckle, or against the floor. And you don't know which way it buckles, whether to you or to me or to the right, to the left. So there is no uniqueness. So it shows that this problem cannot be described within the linearized theory. So you need something more complicated and more difficult. And in fact, it was a huge problem in the 50s because there were many models of rubber-like materials for car industry, for tires, that were modeled via W's of various kind, and there was no convexity, and people were searching for minimizers, and it was a problem. So there are two names behind it. So it's a Rivlin and Mooney. So these are two men. Both are members of the Rubber Research Hall of Fame. So, you know, there are various Hall of Fame for basketball players, ice hockey players, but also for the rubber research people. So it's in the 50s. And then people were trying to generalize the theory for functionals which are not convex. And so what you could exploit, and what we haven't exploited yet, is that the integrand contains a term which is a gradient of some deformation. So there is a special structure. It's not a general functional, but it has some form. So we can exploit it. So we know that J of y is the W of gradient of y of x dx. So we would like to go back to convexity as close as possible, or maybe this doesn't. And on the other hand, we know that this is not possible for W. So in fact, it already happened in 1952 due to Morey, and then special case, and then 1977, John Ball. Who observed that some special functions of gradient of y minor, so determinant and the cofactor matrix of the gradient, have some special properties. So it was Morey for very special function, but the physical interpretation and generalization come from John Ball in 1977, and there's the notion of polyconvexity. So polyconvexity is defined like that. So definition. We say that W, which is now defined on matrices, so I do it in R 3 times 3, but you can also do it in M times N if you want, to R unified with plus infinity, is polyconvex if there is a convex and lower semicontinuous function H, which goes from R19 to R unified with plus infinity, such that W of F can be written as H of F cofactor of F and the determinant of F. So now I recall that cofactor is a matrix of 2 times 2 subdeterminants of original matrix F. And because here we are working mostly on invertible matrices, because we have this property. So if F is invertible, if F is invertible, then cofactor of F is determinant of F times F minus transpose. So this is a matrix which you use if you, in the first semester, you do the inverse matrix calculation. And otherwise, it's a matrix of 2 times 2 subdeterminants. You know the determinant, and F is here. So it's a convex and Laurent semi-continuous function. And so, so it has a flavor a bit of convexity because of this H. And on the other hand, you have these 2 extra terms here. So first of all, what we see is, so properties. So what we see is that convexity implies polyconvexity. Because if by chance I take W convex, then I take just H depending only on F, like the same like W, and I forget the dependence on cofactor F and the determinant. Vice versa doesn't hold because otherwise it will be equivalent. And then you can imagine that you have W of F is, for example, determinant of F. And then this is polyconvex. Now this will be in the, I put it in the definition because I will need it. Like before we had convex functionals, which are Laurent semi-continuous in strong topology. This will help us to show the existence of minimizers here. So, you mean, yeah, so if I have convex, if you give me a convex function, I can also consider it like a polyconvex function. You take, because you take H would be the same like W, and you forget the dependencies on these 2. Because convex functions are even continuous if they are finite valued. We don't have. So we assume this. So we have to assume this. You know, so this is like the extra assumption. If you want to forget it, then you forget this plus infinity, and then you just forget Laurent semi-continuity. Because convex functions are continuous, so they are Laurent semi-continuous. So you give me W convex. So you take W convex. I take H of F equals W of F. And I don't do anything. So this H will now have 2 empty, there will be no variable for the cofactor and no variable for the determinant. And because your function is convex, finite valued, so H is also finite valued and continuous. Convex functions are continuous. I mean, I will need, we need it for physics, simply to be able to include this condition. But if we say, you can also forget about physics, and you just look for Laurent semi-continuity in the weak topology, and you say, we speak about polyconvexity in general. And maybe if you want to apply to mechanics, then you add some extra assumptions. But we can also forget mechanics and just say, take a polyconvex function. And this will tell me that I can prove something for that, like existence of minimizers and in particular our semi-continuity. No problem, that's good that you ask. So this is an example of a function that is not convex because the determinant is not a convex function, and it's polyconvex. It's polyconvex, so this implies but not convex. So it's really a generalization. And I tell you the dream is the following, that if I, if I have my functional j of y, so this is now the integral over omega, and there is w of gradient of y of x dx. And now if my w is polyconvex, I can also write it as the integral over omega of h of gradient of y of x or factor of gradient of y of x and the determinant of gradient of y of x dx by definition. So now this is a convex function, so I'm a little bit like back in my convex scenario. Remember we had this f of x and u and so on. So now the point would be, can we use this somehow? So if I have a sequence which weakly converges in some Sobolev space, I also would like that these guys are converging weakly to the limiting function. And it looks a bit hopeless because this is a quadratic polynomial, this is a cubic polynomial. And we know that weak convergence and nonlinearity typically doesn't go together. I mean, just to give you an example, you can think about a function which is -1 and 1 here. So you take something which oscillates between 1 and -1. So you take a sequence zk, which will be 1 in the interval between 0 and 1 over k. So this will be 1 over k. This will be 2 over k. So the zk would be like that, oscillating between 1 over k and between 1 and -1 on the interval of the size 1 over k always. So this will be my zk. It's a sequence which is bounded in L2 or in L infinity, and you go up to 1, say. Then zk goes weakly to 0 in L2 by the definition. It never takes a value 0, it only takes values +1 and -1, but in average, the weak limit is the average, and this is 0. But then you take a little nonlinearity. You just take the modulus. And the modulus is constantly 1 because you flip the lower part up. So the modulus doesn't converge weakly to the modulus of 0. So even a little nonlinearity like absolute value can destroy the convergence along the weakly converging sequence. And now we want to require this property for these polynomials. But still, we are lucky in this case that this will really work in this setting. So this was the example that weak convergence versus nonlinearity. So, but there is a result like that, so which would help us. So the result is the following. So proposition let yk converges weakly to y in W1 P of omega R3. So omega is a Lipschitz domain, bounded Lipschitz domain in R3. That's my sponge. Omega is a bounded Lipschitz and we have to say what's P. P is bigger than 3. Or if you do it in general dimension, there's n here, and omega is an n-dimensional subset, then you need P bigger than the dimension. Then the miracle occurs, and this is that determinant of grad yk converges weakly to the determinant of grad y in. Now these are numbers and cubic polynomial, so you take LP divided by 3 of omega. So this is the result which holds, and a similar result holds also for the cofactor. And I can say here that the cofactor of gradient of yk, which is a matrix, it's a matrix, goes weakly to the cofactor of grad y in. Now it's better, it's LP divided by 2, because cofactor is a product of 2 elements of the matrix, omega, and now this is a matrix, so it goes to matrices. Sk goes to infinity. So let me just give you an idea why this is possible, because it looks quite unlikely from the first glance. And to do the example, we go to 2 dimensions because it's easier to calculate the determinant. So assume that we work on R 2 times 2. And then, so we write the determinant of the gradient of y is dy1, dx1, dy2, dx2 minus dy2 dx1. That's the definition. And so you can also write it like you take d dx1 here. You have smooth map, so everything is smooth. I can do these operations. So I take y1 here, and I take dy2 dx2. So the first term is fine, but I have a term y1 and the second derivative. So what happens here if I do the following? I take y1 dy2 dx1. So I lose it in the second term. So now this is fine. So this already is very interesting because you can also put plus here, minus here, and it looks a little bit like a divergence. So this is the first term of the vector field, first component. This is the second component. And it's a divergence. And it will be very, very helpful to that. So now, if you do the, you take a sequence which weakly converges. So you take the determinant. So how shall we do this? I mean, you would hate me because if you make nodes, then people don't like it. But I put k here. Now the index will go up simply because I have this is already here. And then I put k here. You know what? I do it completely from the beginning because it doesn't really bother you too much with this. So I want to do the V convergence. So what I will do, I take the determinant of grad y, x, and I take some test function phi of x, and I take a sequence yk. And I want to look at this. So for the determinant, I will do this. I will write the determinant like this. So I write it like the integral over omega d dx1. Now there will be y k1 dy k2. This means the second component dx2 times phi plus d dx2 minus y k1 dy2 k2 dx1 dx. So what you do now, because this is a test function, so phi will be a smooth function with the zero boundary conditions. So I don't have the boundary terms. And I take the derivative here and put it to the test function. This is the role of test functions, to help with derivatives. So you do this per part testing. You get a minus minus, and then you get yk1 dyk2 dx2, and then you multiply this by d phi dx1, plus, you do the same thing with the other. So this will be y k1 dy k2 dx1 times d phi dx2, and the whole thing dx. And now this looks much better, because here I have only the function, here I have the derivative. I have this convergence in the Sobolev space, and this brings me some strong convergence by the embedding of the function values. Now P is bigger than the dimension, so it means I even have continuous function uniformly, and it's a uniform convergence. So this goes uniformly to the limit. The derivative goes weakly. So we have a strong convergence, a uniform convergence times the weak convergence. And this already allows me to pass. This is a test function which is fixed, smooth, and the same thing here. So here in these two terms, I can pass to the limit. And I get exactly the same terms without k. With the embedding and the weak convergence. So there's a interplay of the strong convergence or uniform convergence in our case and weak convergence. While here, if you look at the original form of the determinant, this was weak convergence times weak convergence. And it usually doesn't work. So this was, and the trick was that the determinant can be written as a divergence of something. So this goes for k going to infinity to the same integral without k. And this is exactly what I have. So and then what I do at the last moment, I put the derivatives back to the, I release the test function, and I put the derivatives back to the y functions, and I say this is my determinant. So this is, and with the cofactor, you can imagine it's very similar, because again, this is like a matrix of subdeterminants. If you do it in 3 dimensions, then you do it first for the cofactor, and then you develop the determinant along the row as a cofactor times the matrix value, the matrix entries, and then you have a cofactor goes weakly, and then again you do this per partes and or integration by parts and this divergence of the structure of the divergence. So yeah. So this is somehow how this goes. And I mean, we will not show this, but I mean, determinant and cofactor are the only functions a part of some linear combination of those and the function f which have this property in 3 dimensions. So these are called Null Lagrangians, cofactor, determinant, and f, or the gradient. And these are the only building blocks of functions which have this property, which is called weak continuity of the determinant and of the cofactor. Because this is something very unusual, and this will help us in the proof of our semicontinuity. But you can already anticipate that if you have a convex function, now this goes to the right limit here, that we simply transform the problem to the original proposition with convex functionals. Well, I can look at this triple like at some element of some other space, and this goes weakly to the limit. And this is a convex function. So you, instead of working in 3 times 3, you work suddenly on R19, 19 is there because you have 9 components here, 9 components here, and here 1. So you work in a higher dimensional space. And I think I would stop now because it's almost half. So.